All right, welcome to Calculus, and we're going to do some integration with some rational expressions. And there's a number of different ways we can go about doing some of these. We'll start off, let's just think about one of the underlying problems we run into. So let's just say that we do the integration of x cubed plus x over x minus 1, right? And then dx there. Now, if we go through and we try to do a substitution on this, and I'll let you pause and kind of do that on your own, but a substitution is not going to work here for a number of different reasons. One of which is that if we try to do a substitution on this, what will happen is we won't get the items to match. We won't get the du out of here. There's nothing we can pick for u in order to make it match up with the bottom. If we try to integrate by parts, we run into a similar problem where, yeah, the top piece may eventually degrade away, but we are making the bottom piece further and more complicated as we go through, so we start running into problems with that as well. So we still need to deal with the overarching idea and issue that we're running into with this. So what do? So this is what we do. There are two approaches we're going to take with these functions. The first of one is we're just going to do the long division on this. The second methodology we can go about this is integration by partial fractions, which we'll do another example with here shortly as well. To do the long division of this, and you can look up long division as a whole separate topic, but the quick process here that we do is we just quite literally, and you can also do synthetic division as well. We're going to divide by x minus 1, and here we have x cubed. We're missing the squared term, so I'm going to write x, 0x squared, and then plus x, and then plus 1, right? Not plus 1, I'm sorry, plus 0. Okay, because those are the pieces that we're missing, those two pieces, so we got to keep those placeholders. So x goes into x cubed, x squared times, which gives me x, let's see here, so that's x cubed, and then x squared times 1, right? That gives me minus x squared. I'm going to subtract off that line there, and that's going to cancel the x cubes, and that's going to give me x squared. I pull down my next term of plus x. And then I do the whole process over again. So now I'm just going to multiply by x, which gives me x times x, which gives me x squared. So the thing I'm doing here is I'm taking this piece on the top, okay, and multiplying by the piece on the left here, and that's giving me the new line at the bottom here. So then x times 1 gives us minus x. Once again, I'm always going to subtract off that line I created by multiplication. The x squared is canceled, and now I'm left with 2x. Again, bring down the next term, which in this case is just 0, right? And then when I do this process, right, I'm going to do, let's see here, so plus 2, so 2 times x gives me 2x, and then 2 times negative 1 gives me minus 2. And once again, you subtract off that row, that piece there, and that gives you 2. X won't go into 2, so this is your remainder. So what I now know is I can rewrite this rational function by using what I have in what would be my result here, my quotient here, as x squared plus x plus 2 plus 2 over x minus 1, all that dx'd, right? This gives me a much simpler and cleaner way to do that integration. So the integration of x squared is x cubed over 3. Integration of x is x squared over 2. Integration of 2 is 2x. And the integration of 2 over x minus 1 is 2ln of x minus 1. And then the whole thing plus c. Now, if you want a little bit more of a detailed piece of what's going on with this last part, you let u equal x minus 1. du would be equal to 1 dx. So this, I'm going to pull this out in red here, this piece right here is the integration of 2 times du over u. Well, du over u is by definition, that integration is ln of u, where we already know what that u is, so we just replace it back in here. So here's one way that we can do this, and keep in mind that this particular process is dependent upon an important piece here, namely, that important piece that is dependent upon is that the degree of the numerator is indeed larger than the degree of the denominator. And that's an important thing to remember as you go through this, okay? Now what? All right. So what else can we do? Well, let's do this. Let's do another problem, but let's just do this one by integration by parts. Not parts, I'm sorry, by partial fractions. So let's say we're doing the integration of 2x plus 6 over x squared plus 3x plus 2, and my dx to designate what variable I'm using here. Now, once again, I'm going to encourage you to, you can hit pause for a second here, and you can see that substitution doesn't work and integration by parts doesn't work here. If you did this by parts, you would have to let one piece be 2x plus 6, and the other piece would be 1 over x squared plus 3x plus 2. And regardless of which way you do that, you're going to run into problems in either direction with doing either the derivative or the integration of either of those. That's going to create more problems. So try those out real quick just to prove to yourself they do actually cause you to have some issues. So let's look at what else we can do. Let's do partial fractions here. So I'm just going to remove the integration sign just for a second. Okay, well, maybe more than a second. And we're going to set this up with partial fractions. And the idea is that we're going to split this up into two separate fractions. And I say two separate fractions because my denominator is a quadratic, meaning it has a degree of 2. That degree tells me how many of these new subfractions I'm going to have. I don't know what these numerators are, but I know the denominator is going to be the factorings of the denominator, one in each place. So this denominator factors into x plus 1 and x plus 2. Now I'll give you a second. You can take a moment and prove that they do actually multiply out to that. Remember, you multiply to something that gives you the last term and adds to the center term. And the next question you're asking is, which one do I know comes first? And the answer is it doesn't matter. It can be a over x plus 2 and b over x plus 1, or as I have it written. Just keep it consistent through the problem, so don't switch it up as you go through. Now, here's where it gets fun. I'm going to think of this denominator here as x plus 1 and x plus 2 because it's going to be more useful to me in its factored form. And what I'm going to do is I'm going to multiply the right and the left-hand side of this by those denominators. So I'm going to multiply the right-hand side and the left-hand side by x plus 1 and x plus 2. Do the same thing on the other side. X plus 1 and x plus 2. Now, just kind of explain a couple pieces that are going on here with this. I factored out the original numerator, and then I set it equal to a over x plus 1 and b over x plus 2. I can do that because I have the right to set it equal to something, especially when I have two unknowns in there, like a and b right now. Okay, and now I'm just multiplying it by both sides of the equation by the same thing. What's going to happen on the left-hand side is that cancels it completely, and now I have 2x plus 6 is equal to, now what's going to happen is I'm going to take this piece and multiply it to that term and to the second term, to the a term and the b term. And when I do that, I end up with a times x plus 2, x plus 1 over x plus 1, and b times x plus 1 and x plus 2 over x plus 2. Some of you may be thinking, well, you changed the order in how you wrote those. That was just an error on my part. Don't read too much into that part. But what I do now have is I have these pieces here and the x plus 1s that cancel. All right? And now that they cancel, I have 2x plus 6 is equal to a times x plus 2 and b times x plus 1. Now, once I have that, I'm almost ready to go back and figure this out. So what we're doing here is we're doing a lot of algebra so that we can make our calculus simpler. Okay, that's what we're doing here. So now what I'm going to do is I'm going to pick a value for a. No, I'm going to pick a value for x. I'm going to pick x to be equal to -2. And some of you are thinking, you can just pick that to be whatever you want it to be. Yes, you absolutely, completely can. I can pick it equal to 0. So now the next question is, some of you are saying, well, why did you pick it to be negative 2? Because negative 2 is going to be useful to me. Watch. I do 2 times negative 2 plus 6 is equal to a times negative 2 plus 2, and b times negative 2 plus 1. Negative 2 plus 2 is 0. It gets rid of a for me. So the only unknown in this entire sentence here is b. So what I have here is negative 2 times 2, which gives me 4, negative 4, plus 6, which gives me 2. And then I end up with negative b. So b is equal to negative 2. You can pause and do that algebra process if you need to. Okay? So I just figure out the value of b. Now I go back and I pick a value for x again. So I'm going to pick x to be equal to, you guessed it, negative 1. So I get 2 times negative 1 plus 6 equals a times negative 1 plus 2 plus b times negative 1 plus 1. Again, that entire term, that b term ends up being 0 for us, which is nice. And now I plug in all those, or evaluate all those pieces I have. Negative 2 times 1 gives me negative 2 plus 6, which gives me 4. And that means that 4 is equal to a. Now, I have my value for a and I have my value for b. Going back up here at the top, I have a over x plus 1. So that is 4 over x plus 1. And I have negative 2 over x plus 2 right there. All right. And the thing was, I had the integration of 2x plus 6 and over x squared plus 3x plus 2 dx. That's now equal to the integration of 4 over x plus 1 dx plus the integration of negative 2 over x plus 2 dx. And I'm almost home free at this point. All right? So on this first one, if I let u equal x plus 1, that means that du is equal to 1 dx. So what I'm really dealing with is 4 times du over u, which is ln of u. So that's 4 ln of x plus 1. Do the same thing to the next one. So I get negative 2 ln of x plus 2. And then plus c on the end of that, because both of these would have produced their own constant. The constant plus a constant is still a constant. So I just have one constant for the whole thing. And there are other ways that you can write this, of course. One of those is the subtraction of two logarithms is the division of their interiors. And then, of course, you could write the pieces in the front there as their powers. So I can write this as ln of x plus 1 to the 4th power divided by x plus 2 raised to the 2nd power, all that plus c. Okay? And there's that integration. So, pretty straightforward. It is not a short process. It is, by all accounts, I do believe it is a fairly straightforward process, although it does take some practice just to get it down so that you understand how to do it properly. If you need more examples about this problem or any others that you come across in my videos, or you found another video by another individual and you say, I need to know more about this topic, I'm more than happy. Just send me a comment or an email asking for additional support on those problems, and I'll be more than happy to post those as quickly as I can. Take care. Have a good day.